All right. Yes, it does say days 12, but you used to combine days, but it's actually just day 12. Let's go red. So yeah, there, day 12. Day 12 continues more of kinematics. So here we go. Direction. Telling direction, rather. Whenever an object is accelerating, and if the acceleration is acting in the same direction as the motion, the object's velocity increases. So this would be like a vehicle, and it's speeding up this way. Um, so it's speeding up. I'll just put speeding. It's speeding up in the same direction that it's moving. Displacement. So because of that, we know that it's going to have what's called a positive acceleration. And if the acceleration is acting in the opposite direction, so let's say it's braking, then your object's velocity will decrease. So the acceleration could be in two different ways. We do sometimes say the word deceleration, but it's better to say like a negative acceleration. Um, so people usually say that objects are speeding up or accelerating, and then slowing down we say decelerating. And yeah, we should probably say positive and negative acceleration. To be more exact, decelerating is not really a physics word, although I use it sometimes because, using the same word over and over again gets kind of annoying, and humans want to use synonyms sometimes. So, a couple of kind of situations. If the signs are the same, meaning you're accelerating and your velocity is positive, or if your acceleration is negative and your velocity is negative, the object speeds up. This one makes sense. It's a car speeding up. This one doesn't as much. But you could think of it as you're backing out of a parking space really fast, and so you hit the gas as you back out, while your acceleration is going backwards, and so is your velocity. And you're speeding up, because remember, speed does not care about direction. You're just speeding up going in the opposite way. If the signs are opposite, meaning you have a negative acceleration or a positive velocity, or a positive acceleration and a negative velocity, the object is slowing down. What kind of situations would these be? Well, let's say you're driving on a road and you see a deer in front of you and you brake. Well, your velocity is still positive because you're still going forward. But your acceleration is negative because it's trying to stop you from hitting the deer, or rather, you're trying to stop from hitting the deer. Another example is you have a positive acceleration but a negative velocity. So you're backing out of the parking spot, and then all of a sudden, a little kid runs out, and you see on your backup cam, oh crap, I don't want to hit the kid, and so you hit the brakes. So when you hit the brakes, you're still going backwards, but you're hitting the brakes so that you're not going backwards as fast, and so you have a positive acceleration. So those are kind of two opposite type situation. But this note that this does mean that negative acceleration does not always mean that an object is slowing down, and that a positive acceleration doesn't always mean it's speeding up. So just kind of careful with the vocabulary. So we'll do an example. If we use the plus and minus signs to indicate the directions of velocity and acceleration, in which the following situations does the object actually speed up? Well, if you have a positive velocity and negative acceleration, that's like you're braking for a deer. A negative velocity and a positive acceleration, that's the backup cam situation where you're backing up and then you slam on your brakes because you don't want to hit a kid. A positive velocity and zero acceleration, well, this is just this is just cruise control. That's all it is. Because you're not accelerating. And a negative velocity, negative acceleration, well, remember when they go in the same direction, then you're actually speeding up, and so your answer is D by default. Okay, cow. Amazingly, there's a lot of pictures of cows in cars on the internet out there. This one's from Siberian Times. I guess that's one way of transporting your cow. But let's say this cow is undergoing a constant acceleration, has initial velocity of 26 and a final of 12. What's the average velocity? Well, you know that an average is any initial plus any final, or really just any two, divided by but 2. And so all I got to do is take my 26 plus my 12, which gives me 38. Divide that by 2. 38 divided by 2 is going to be 19 meters a second as my average velocity. So average velocity is probably one of the easiest things to find. Um, if we ignore air resistance, the acceleration of an object that is falling downward is constant. How do you suppose the acceleration would change if we do not or ignore air resistance? Normally I ask you this like personally in class, but obviously it's not going to happen. The acceleration increases. The acceleration does not change. The acceleration decreases. There's not enough information to say. Well, the acceleration does not increase because the value, as you looked up in the last class, for the acceleration due to gravity is around 9.8 meters a second squared. And you're not going to fall far enough generally for that value to change. And so it's not definitely going to increase since it's a constant acceleration. The acceleration does not change. Well, that would be true if we ignore air resistance, but air is an opposing motion. So it's definitely going to oppose it, and it's going to actually decrease it until you reach a terminal velocity. Terminal velocity occurs when the upward drag is balanced by your gravitational weight. And then you fall at a constant speed. So really, you decelerate from 9.8 all the way down to 0. Let's say you jump out of a plane until you're at a constant free fall. So we always ignore air resistance, and even like in the calc-based physics, you may do one or two problems where you factor it in, but it's a lot more complicated because it's like you'd have some sort of final velocity minus or equals some initial velocity plus your acceleration times time, and then there's some sort of like a BVI squared or something like that. Basically, it's really weird, and this B is like one of your drag coefficients, and it gets pretty complicated. And there's really no way, because we don't know if it's going to be BV or BV squared half the time. It kind of depends on a lot of different factors, but yeah. Not a lot is done when you actually use calculate with we just don't do a lot when we calculate using air resistance. Okay, so more on acceleration due to gravity. All objects falling near the Earth's surface have an approximate same constant acceleration of 9.8. It does vary a little bit in that the Earth is not a perfect sphere. It's more oblong. So that if you're at the equator, you're actually further away from the center of the Earth. And so at the equator, you're going to have a slightly smaller gravitational acceleration. And at the poles, you'll have a slightly higher acceleration. And I think I've mentioned that before, how you would weigh a little bit more in Anchorage than you would in Honolulu just because of the proximity to the center of the Earth. But it's around 9.8. It's like exactly like 9.80, I think, in Wichita. If we're treating up to be positive and down to be negative, we're generally going to consider it to be a negative 9.8. Why? Because the negative denotes that it's always pointing towards the center of the Earth. So it's going to be negative up here, it's going to be negative down here, it's going to be negative here. It's always pointing the center of the Earth. Towards the center of the Earth, sorry. And we always are going to ignore air resistance, but just keep in mind that for large objects it's probably fine, but like for small objects like an ant that hits its terminal speed really quickly, or even a raindrop, doesn't really apply. All right, so we'll do a problem. Point of rocks. This is in western Kansas, far southwestern Kansas, like in the bottom southwest corner. But when you're standing on top, you can see like the ruts from the old Santa Fe Trail, and it's around 90 feet tall. It's really pretty out there. Let's say you drop a rock off of it. How far will it fall during 2 seconds? So, all right, what do we know at this point? Well, we know if we drop it, our initial velocity. That was weird. Our initial velocity is going to be 0. And we also know that delta x is equal to vi plus vf over 2 times delta t. We know that the time is going to be 2 seconds. We're looking for this value. We know that this is 0, but we don't know our final velocity. Okay, well, what are we going to work with now? Well, okay, from last class, we know that the acceleration is the change in velocity over change in time. Or I can say that that's Vf minus Vi over delta t. If I multiply both sides by delta t and then move my Vi over, I get Vf is equal to Vi plus a delta t. This will be one of the equations I give you. It's not, why do I do it this way? It's the same thing as the definition of acceleration that you found from the graph. Just sometimes it's easier to work with, and I can use it for a later on proof. So this is all this is definition of acceleration. Well, why do I want this? Well, because we know that we need to find our final velocity to get how far it's going to fall in 2 seconds. And so the only way we're going to do that is by using this equation. Okay. Because we know this is 0, and we know the acceleration. Oh, what is the acceleration, by the way? Oh, yes. It will be negative 9.8 meters a second squared. Now we can do that. So I take VF, and that's equal to a negative 9.8 meters a second squared. And then that's times 2 seconds. So that'll give me a final speed, or sorry, velocity in this case, of negative 19.6. It's negative, and it should be, because if you drop it, the velocity should be going down. Now that I have the final velocity, I can plug it into that to get my equation, or my distance. And so I take that, and I put negative 19.6 meters a second, divide that by 2, and then all time 2 seconds. Once again, I'm using this up here. Your seconds cancels, giving you unit of meters, and your 2's cancel, which then gives you negative 19.6 meters. Why is it negative is your first question. Well, because it's going down 19.6 meters. Second question is, well, they gave me the height over here. Why didn't I use that? Well, because I wasn't trying to find the total time it takes to fall all the way off the cliff. I just want to know how far it would actually fall in 2 seconds. And so because of that, I didn't actually use that value. Anywho, and eventually we'll have an equation that combines both of these, but for now we just kind of do them separately. Next up is an air conditioning problem. An air conditioner is dislodged from a window 4 meters above the ground. With what velocity would the AC unit impact the ground? When you look up air conditioning pictures, I found all sorts of fun ones. This website, Northwest Plumbing, it's just some company that published a bunch of how not to install air conditioners, and it's got all sorts of fun pictures of people not doing things wrong, which I kind of found entertaining when I found it. So I figured I'd put a whole slide of those pictures, because usually if it's about an air conditioner, I'll put a picture of an air conditioner. Most know what that looks like, but sometimes I do teach classes with like international students, and then they don't really know what something is, and they don't even know what it looks like. Particularly like in Physics 1, flywheels, people don't know what that is. And so I always try to put a picture of what we're talking about to give them an idea. And that's something else you probably should think of in the future. Like if you got kids with, it should be like an ESOL class, it might help to put pictures there so they at least have an understanding of what's there. Anywho, air conditioner, dislodged, 4 meters above the ground. What velocity will it impact the ground? Okay, so this time we know it's going to fall the full 4 meters. So my change in distance is going to be a negative 4 meters. And we know it accelerates due to gravity at negative 9.8 meters a second squared. We're trying to find the final velocity the AC unit impacts the ground. So this is where I'm going to say the VF is equal to VI plus A delta T. We know it's dislodged, so it just initially falls. So our initial velocity is 0. And we know the acceleration is negative 9.8, but we don't know time, and we don't know VF. So we can't really use that at the moment. So I'll go back to delta X is equal to, for initial velocity is 0, plus our final velocity, divided by 2 times delta T. Well, in here, I know the displacement. I don't know the final velocity, but I do, and I don't know the time. So I also have 2 unknown variables. So just like with the problems we did with, or 2 different people driving, leaving at 2 different times, going the same distances, we had to combine those equations. Well, that's what we're going to do. So I'll take my delta X equals, and the VF, I'll put this in parentheses, was just A delta T over 2 times delta T, or delta X is equal to, I'll simplify this, 1/2 of A delta T squared. This isn't an equation really necessarily to use. This is just built for this one instance. So keep that in mind. But now I know that this is going to be negative 4 meters. the acceleration is going to be negative 9.8 meters a second squared. And then this is delta t squared. Okay, well, meters, notice, will cancel out on both sides, and that leaves me a unit of seconds squared, which is not quite what we wanted, but it's actually okay. The negatives also cancels, and we get positives on both sides. And so, okay, this is 4.94. And then I'll write this out as 4, and then moving my second squared up to the top over 4.9 is equal, that's weird, delta t squared. All right, so when you get to this point, it may have been a while since you've had college algebra, you take the square root of both sides. And when you take the square root of 4 over 4.9, which I need to put in my calculator now, up to this point I've been able to do everything in my head. Yay. You get 0.90, or just 0.9 seconds. And when you take the square root of seconds squared, you get seconds. And so we get a change in time of 0.9 seconds. So our units work out, and now I know at least the time it takes to hit the ground. But you're saying, well, we want velocity. Well, that's fine. We just can come back up to this original equation right here and find the final velocity. Oopsie. Okay, so then we take my final velocity. And then we know the initial was 0, so I'll take my negative 9.8 meters a second squared. And then I'll take it by 0.9 seconds. And so I multiply that by 9.8, and I get a negative 8.85. Okay, so it's negative because it's a velocity, and the negative also says it's going to point downward when it hits. And so out of all of these, if I asked for speed, it might be positive 9, but I didn't. I said velocity. So our answer is going to be D, a negative 9 meters a second. And that is it. I shall see you in class on Monday.